In the next few slides, we'll show an example of the difference between linear and circular convolution. Let's see this example. We have a aperiodic sequence x of n that only has two samples, time 0 and time 1, with the rest 0, and a h of n with only three samples, with everything else 0 outside this interval 0, 1, 2. Let's call this impulse response ABC and the input 1 and 2. We know that in the time domain, what we are trying to do to get y of n is the convolution, we should say linear convolution between x of n and h of n by this equation. And since this x of k has only two samples, we only are actually interested to do this operation with x0 times h of n minus 0, x of 1 times h of n minus 1. These two operations. Because the rest of the xk's are 0. And now let's clearly understand what's going on between these two. H of n is this guy. H of n minus 1 is the delayed version of this guy. So this is h of n. And we are multiplying by x of 0. What is x of 0? It is 1. So this is ABC. X of 1, which is this guy, number 2, multiplied by h of n minus 1, a delayed version of h of n. So basically, instead of time is 0, 1, 2, now time is 1, 2, and 3. And all the values of ABC is now scaled by 2. So we are just adding these two guys up, and this is the answer. A at time 0, at time 1 is B plus 2A. Time 2 is C plus 2B. Time 3 is 2C. So this is normal convolution, and this is what we need. Now, if you try to use DFT to realize convolution, we are actually doing circular convolution, as mentioned in the last slide. So in circular convolution, you would think that since we have h of n to be 3 samples, then we're going to take 3 sample DFT. So you can simply take DFT of 3 samples. You can get h of k. Here is 1, 2. Well, the last sample we pretend that is 0. So it's 1, 2 followed by 0. So we make a 3 sample x of n, and we can take xk. So now is a 3 sample DFT. With a 3 sample DFT of h, we can multiply them together and get yk, which is also 3 sample. You take inverse Fourier transform, then you are actually doing this. You are doing circular convolution, denoted by this sign. I clearly indicate n equals to 3 means that we are 3 sample periodic. Now, you basically then, what we have just done is not linear convolution anymore. It is called circular convolution. Circular convolution, this equation, is also about the same as this previous equation that we mentioned here. Here, the tilde says that this guy is repeating. Here, to make him repeat, we are using this symbol, and we are saying that it is rotating with 3 samples. What do I mean? Well, this is h n tilde. What happened when we delay by 1 sample, n minus 1? Actually, this 3 red thing is going to move right, and this green thing is going to move into time 0. And then it's going to multiply with xk. This is where the problem occurs, because there are samples before time 0 getting shifted in. You look at the linear convolution. When we are delaying by h of n minus 1, 0 is being shifted in. Now we have the green period prior to the red period being shifted in. So this is the reason why circular convolution is different to linear convolution. Circular convolution occurs because h of n is periodic, and this periodicity, even though it didn't exist in the real h of n, arises because we took the DFT of h of n. Now, we want to overcome this. We want linear convolution, but we are only able to do circular convolution when we use DFT. What can we do? Well, let's try. Let's try using n equals to 4 instead. So if n is equals to 4, what we mean is that we are padding h of n with extra zeros. And when we pad h of n with extra zeros, zeros get shifted in. That's the idea. So let's see the result. X of k times h of n minus k. Now we are pretending that we are using 4 samples worth of h of n. H of n was 1, 2, and 3, padded by 0. This is h of n. H of n minus 1, when we try h of n minus 1 with a 4 sample sequence, 0 is being shifted because the previous period have a 0 at the end. So when we delay this guy, the 0 is being shifted in, and we get 0, 1, 2, 3. So this is h of n now. This is h of n minus 1. So the cool idea is that if we want to push in zeros into hn minus d, we basically extend h of n and pad them with zeros. And now, even though when we do DFT, the answer is correct. You may ask, what about if we pad more zeros into h of n? So when we pad more zeros in h of n, this is h of n. H of n now is 1, 2, 3 followed by 2, 0. In the past, it was 1, 2, 3 followed by 1, 0. This is the 4-point DFT. This is the 5-point DFT. So what happened? Well, actually, when you are doing this, because x of k only has 2 values, we are only delaying it twice, x0 and x1. Delaying by once, not delaying by any sample, and only delaying by one sample. So it has no effect whatsoever. The answer, of course, is that, hey, when you use this in DFT, you'll produce one extra 0 here because we are actually doing circular convolution, and in this case, when n equals to 5, you have 5 numbers here, and theoretically, this 5 number is going to repeat for the next period. While here, it is only 4 numbers, and it's going to repeat 4 numbers. But we know that only these 4 numbers is of interest. 1353, 1353 is the convolution, is the linear convolution between xn and hn. So let's summarize. If we want to perform linear convolution with DFT, what must we do? First, let's discover what is the length of xn. Let's say his length is L, because it's from 0 to L minus 1. And the length of hn is m. So they are of different length. How to do convolution? Well, if we do convolution in this way, we'll get a final length of L plus m minus 1 for the length of yn. So we know that the only important signal is L plus m minus 1. So what do we do? Xn has length L. We pad it with m minus 1, such that its final length is L plus m minus 1. So that's for x. H with length m is also padded, but now of different length. So now the final length is still m plus l minus 1. So the length of this and the length of this are the same. It's capital N. And it is basically padded with different numbers of zeros of x and h. We can then take the DFT of this, the DFT of this, and we got xk and hk. When we multiply together, we are doing circular convolution in the frequency domain. We can take the endpoint DFT and we will get y of n of length n, and it is correct. It is as if it is linear convolution simply because we have padded it with the correct amount of 0. This is the last slide. So in the previous example, when our hn is 1, 2, 3, and when we padded with 1, 0, which is length 4, then we see that the answer is 1, 3, 5, 3. Let's do it using MATLAB. 1, 2, 3 padded with 1, 0. X is 2, length 2, but we padded with 2, 0, so length is equals to 4. So this length is equals to 4. We are using 4-point DFT. So simply we take Fourier transform of, the DFT of H, the DFT of X, we multiply them together. Dot star means we are multiplying element wise, and we perform inverse FFT, and out comes the Y as 4 numbers. Exactly the same as this. Now I can do, of course, convolution of H and X, and you realize it's 1, 3, 5, 3 with zeros after that. So we know that only this guy, 4 points is important because it will be 0 after that. Thank you.